Hello there, and welcome to Zzscience, where the universe's greatest mysteries become gentle companions for your journey towards sleep. We're delighted you've chosen to drift through the cosmos with us tonight. Before we begin our gentle exploration, feel free to share what time it is and where you're listening from. It's always wonderful to imagine all of us scattered across this spinning planet, each looking up at the same starlit sky, wondering about the same beautiful secrets hidden in the dark. Tonight, we're wandering into one of the universe's most elegant puzzles: dark matter. It's the cosmos's ultimate hide-and-seek champion, making up most of everything that exists while remaining completely invisible to our eyes. We'll follow the story of how scientists discovered something they couldn't see, drift through the cosmic web that connects all galaxies, and gently explore why this invisible substance might be the most important thing in the universe. So settle in, let your breathing slow, and let's take a nice slow wander into the dark. Most of the universe is playing an elaborate game of hide and seek, and it's winning. All those twinkling stars scattered across the night sky, the gentle spiral of the Milky Way, the distant galaxies captured by our most powerful telescopes, they represent less than 5% of everything that exists. The rest? It's there. We know it's there, but it's completely invisible, like a cosmic magician's trick performed on the grandest possible scale. This humbling realization didn't arrive with fanfare. It crept up on astronomers slowly, through decades of careful observations and increasingly puzzled head-scratching. Picture scientists in the early 20th century, confident in their cosmic inventory: stars, planets, gas clouds, dust, and the vast emptiness between. It seemed like a tidy accounting of reality, everything visible and accounted for. The universe as a well-organized library where every book was on the shelf. But then they started weighing things. Not with bathroom scales, of course. You can't exactly ask a galaxy to step on and hold still. Instead, they use gravity as their cosmic measuring tape. By watching how fast stars orbit around the centers of their galaxies, or how quickly entire galaxies dance around each other in clusters, astronomers could calculate how much mass must be pulling on them. The way you might estimate the weight of an invisible person, by watching how the seesaw tips. And that's where the mystery deepened. The math kept refusing to add up properly. Stars at the edges of galaxies were moving far too quickly for their own good. According to Newton's laws, which had worked perfectly well for centuries, these outer stars should have been moving much more slowly, or they should have been flung off into space like mud flying off a spinning bicycle wheel after a particularly enthusiastic ride through a puddle. But they weren't going anywhere. They clung to their galaxies with stubborn determination, whipping around at speeds that suggested there was much more mass holding them in place than anyone could see. It was as if someone had secretly loaded extra weight onto a merry-go-round without telling the riders, who found themselves spinning faster than the visible merry-go-round should have allowed. The first hints of this cosmic puzzle appeared in the 1930s, when Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a bustling neighborhood of over 1,000 galaxies, all bound together by gravity. Using those same gravitational accounting methods, he calculated that the cluster needed to be at least 400 times more massive than what he could observe to explain how the galaxies were moving. Being a practical sort with a gift for memorable names, he called this invisible mass Dunkel Materie, dark matter in German. Not because it was necessarily black, but because it didn't give off light. It was matter that mattered, gravitationally speaking. but remained frustratingly invisible to every telescope and detector. For decades, most astronomers politely set aside this uncomfortable result. It seemed too strange, too unlikely to be true. Surely, there was a simpler explanation lurking somewhere. Maybe they were miscounting the visible matter, or perhaps vast clouds of dim gas were floating between the galaxies, too faint to detect with the instruments of the day. The universe, after all, had always been full of surprises, but invisible matter seemed like pushing things a bit too far, even for a cosmos that had already given us black holes and quantum mechanics. But as telescopes improved and observations became more precise, the evidence kept mounting like snow on a quiet winter night. Galaxy after galaxy showed the same puzzling behavior. They all seemed to contain far more mass than met the eye, typically about 6 times more. It was like discovering that every person you'd ever met was actually an iceberg, with most of their substance hidden beneath the surface, calm and mysterious. The breakthrough moment came in the 1970s, when astronomer Vera Rubin began making detailed observations of how individual stars moved within galaxies. Her work would transform dark matter from an obscure hypothesis, gathering dust in academic papers, into one of the most important discoveries in modern astronomy, a revelation that would reshape our understanding of reality itself. But even before we drift into those specifics, it's worth pausing to appreciate just how extraordinary this situation truly is. We live in a universe where the vast majority of matter, the stuff that shapes cosmic structure, influences the formation of galaxies, and ultimately made our own existence possible, is completely invisible to us. It's like being a character in a story where most of the plot is happening off-stage, with only occasional hints and shadows to suggest the grand drama unfolding just beyond our perception. This invisible majority doesn't just sit there passively either. It actively shapes the cosmos, creating the gravitational scaffolding upon which all visible structure hangs, like decorations on an invisible Christmas tree. Without it, galaxies wouldn't form properly, stars wouldn't cluster into the beautiful spiral patterns we see, and the universe would be a much lonelier, emptier place. A cosmic desert where oases of matter would be few and far between. And yet, despite its profound importance, dark matter remains stubbornly elusive. It doesn't emit light, doesn't absorb light, doesn't reflect light. It barely interacts with ordinary matter at all, except through gravity. It's like sharing your house with a roommate who never eats your food, never uses the bathroom, never makes noise, but somehow still influences where you put the furniture simply by existing in the same space. The search for dark matter has become one of the greatest detective stories in science, a cosmic mystery that has absorbed the careers of thousands of brilliant minds and inspired the construction of some of the most sophisticated experiments ever devised. And while we still don't know exactly what it is, every new observation brings us a little closer to understanding this invisible architect of the cosmos, this quiet force that shapes everything we can see. Galaxies, it turns out, have been breaking the rules for billions of years, and it took a patient astronomer with a keen eye to catch them in the act. The culprit was Andromeda, our nearest galactic neighbor, sitting there in the autumn sky like an innocent smudge of light, spinning with such serene confidence that it took decades for scientists to realize it was doing something impossible. The detective in this cosmic mystery was Vera Rubin, an astronomer whose careful observations in the 1970s would revolutionize our understanding of the universe. Rubin wasn't hunting for dark matter. In fact, Hardly anyone was even thinking about it seriously at the time. She was simply trying to understand how galaxies rotate, which seemed like a perfectly reasonable thing to wonder about on a quiet night at the observatory. Picture a spiral galaxy like a cosmic pinwheel, with graceful arms of stars sweeping out from a bright central bulge. Common sense, backed by centuries of successful physics, suggested that stars closer to the center should orbit faster than those farther out, just like planets in our solar system. Mercury zips around the Sun much faster than distant Neptune because the Sun's gravitational pull is stronger up close. It's the same principle that makes figure skaters spin faster when they pull their arms in. Physics, working exactly as expected. So when Rubin pointed her telescope at Andromeda and began measuring how fast stars were moving at different distances from the galaxy's center, she expected to see a neat, predictable pattern. Fast inner stars gradually giving way to slower outer ones, creating what astronomers call a Keplerian decline. It should have been as orderly as a well-conducted symphony, with each section playing at precisely the right tempo. Instead, she found something that looked more like a jazz ensemble where everyone had decided to improvise at the same time. The outer stars, the ones that should have been moving slowly according to all known physics, were racing around the galaxy at nearly the same speed as their inner neighbors. It was as if Neptune had suddenly decided to keep pace with Mercury, which would be quite the astronomical surprise, and probably not very good for Neptune's orbit insurance. At first, Rubin and her colleagues thought there might be an error in their measurements. Astronomical observations are tricky things, full of atmospheric interference and instrumental quirks. And spiral galaxies are complex, messy objects, full of gas clouds and dust lanes that can muddle clean data. But as they refined their techniques and observed more galaxies, the same puzzling pattern kept appearing like a stubborn stain. Galaxy after galaxy showed this flat rotation curve, as astronomers came to call it, instead of the expected decline. The implications were profound, though they took time to settle in like sediment in still water. If stars at the edges of galaxies were moving that fast, there had to be much more mass holding them in place than anyone could see. The visible stars, gas, and dust simply weren't enough to provide the gravitational pull needed to keep those outer regions bound to the galaxy. It was like watching a child on a merry-go-round spinning at tremendous speed without flying off, despite the merry-go-round appearing to weigh only a few pounds. Rubin's observations suggested that galaxies were embedded in vast halos of invisible matter, extending far beyond the visible edges of the stellar disk, like enormous dark cocoons. This matter didn't emit light, didn't absorb light, and didn't seem to interact with ordinary matter in any way except through gravity. But gravitationally, it was enormous. Typically 5 or 6 times more massive than all the visible matter combined, like discovering that most of an iceberg really is underwater. The scientific community's reaction was initially skeptical, which is exactly what you'd expect from a group of people trained to question extraordinary claims and demand extraordinary evidence. Some astronomers suggested that perhaps there were vast amounts of dim, ordinary matter hiding in the outer reaches of galaxies, brown dwarfs, black holes, or clouds of cold gas that simply weren't bright enough to detect with existing telescopes. These hypothetical objects were dubbed MACHOs, massive compact halo objects, which may be the most cheerful acronym in astronomy. Others proposed that maybe gravity itself behaved differently on galactic scales, weakening more slowly with distance than Newton and Einstein had predicted. This idea, known as modified Newtonian dynamics or MOND, suggested that the problem wasn't missing matter, but an incomplete understanding of how gravity works when stretched across such vast distances. But as observations continued and became more sophisticated, the dark matter explanation kept gaining ground like a slow but steady tide. The cosmic microwave background radiation, the faint afterglow of the Big Bang itself, showed tiny fluctuations that exactly matched what you'd expect if the early universe contained both ordinary matter and a much larger amount of dark matter. Computer simulations that included dark matter could reproduce the large-scale structure of the universe we actually observe, while simulations without it failed as spectacularly as a souffle in a thunderstorm. Perhaps most convincingly, astronomers discovered gravitational lensing, the way massive objects bend light like cosmic magnifying glasses. When they mapped these gravitational distortions around galaxy clusters, they found that the strongest lensing often occurred in regions where there wasn't much visible matter, but where dark matter simulations predicted the invisible stuff should be most concentrated. It was like seeing the shadow of something invisible, the universe's way of signing its name in gravity. Vera Rubin's work opened a window into a hidden cosmos, revealing that the universe is far stranger and more mysterious than it appears to our eyes. Her observations showed us that we live in a galaxy and a universe that is mostly made of something we can't see, can't touch, and don't understand. It's humbling and wonderful in equal measure, like discovering that your familiar neighborhood is actually floating in an invisible ocean you never knew existed. Today, Rubin's flat rotation curves are considered one of the strongest pillars of evidence for dark matter, along with gravitational lensing, the cosmic microwave background, and the large-scale structure of the universe. Her patient, meticulous observations revealed that the cosmos is playing a magnificent game of hide-and-seek, with most of the players invisible to our eyes, but visible to our instruments, at least indirectly. And so, Andromeda continues its ancient rotation, unaware that it helped solve one of the universe's greatest mysteries simply by refusing to behave as expected. Sometimes the most profound discoveries come not from finding something new, but from realizing that something familiar has been secretly extraordinary all along. Spinning through space with invisible companions we're only just learning to detect. If you could somehow step outside the universe and look back at it from an impossible distance, which would admittedly be quite the trick, you'd see something breathtaking. The cosmos isn't just a random scattering of galaxies floating in empty space like glitter thrown into a dark room. Instead, it's organized into something that looks remarkably like a vast, three-dimensional spiderweb, with galaxies strung along bright filaments that stretch across hundreds of millions of light-years, separated by enormous dark voids where almost nothing exists except silence and space. This cosmic web, as astronomers have come to call it, is one of the universe's most beautiful and mysterious features. And according to our best understanding, it's built almost entirely from dark matter, with ordinary matter, the stuff of stars and planets and morning coffee, simply following along like colorful ribbons tied to an invisible framework. To understand how this grand structure came to be, we need to drift back to the very beginning, to a time when the universe was young, hot, and remarkably smooth like cream in the coffee before the first stir. In those early days, just a few 100,000 years after the Big Bang, matter was distributed almost uniformly throughout space. Almost, but not quite. There were tiny fluctuations, subtle variations in density that showed up as faint hot and cold spots in the cosmic microwave background radiation, like barely visible ripples on an otherwise calm pond. These fluctuations were minuscule, variations of just 1 part in 100,000, differences so small they'd be like noticing that 1 grain of sand in a beach was slightly larger than its neighbors. But in a universe governed by gravity, even the smallest irregularities have a way of growing over time. Regions that were slightly denser than average had a bit more gravitational pull, which attracted more matter, which increased their gravity further, which attracted even more matter. It's a cosmic version of the rich getting richer, with gravity as the bank that always pays compound interest. Dark matter played a crucial role in this process because it could start clumping together much earlier than ordinary matter. In the universe's youth, ordinary matter was far too hot and energetic to settle down anywhere, like trying to herd cats made of lightning. Electrons and protons zipped around at tremendous speeds, constantly being scattered by radiation in a cosmic game of pinball that never ended. It was like trying to build a sandcastle during a hurricane. The pieces simply wouldn't stay put long enough to stick together. But dark matter, as far as we can tell, doesn't interact with radiation at all. It could ignore the cosmic chaos and begin the slow, patient work of gravitational accumulation, like a Zen master meditating in the middle of a bustling marketplace. Dark matter particles drifted toward regions of higher density, gradually building up the gravitational wells that would eventually capture and hold ordinary matter once it finally cooled down enough to behave. Over millions of years, this process created a vast network of dark matter filaments, with dense nodes where multiple filaments intersected like cosmic subway stations. Think of it as the universe's transportation system. But instead of trains carrying commuters, you have streams of dark matter flowing along invisible tracks, converging at major hubs where galaxies would eventually form and flourish. When ordinary matter finally cooled enough to settle down, an event astronomers call recombination, though it sounds more like a cosmic support group, it fell into these pre-existing gravitational wells, like water flowing into a series of connected valleys, carved by an invisible river. The largest concentrations of dark matter became the sites where the biggest galaxies formed, while smaller clumps hosted smaller galaxies or remained dark and invisible, cosmic ghost towns waiting for residents who never arrived. This is why galaxies aren't randomly distributed across the sky, like stars scattered by a careless hand. They follow the underlying dark matter structure, clustering along filaments and avoiding the vast empty regions called voids. If you could somehow make all the dark matter visible for just a moment, the universe would light up in a spectacular web pattern, with galaxies marking the densest intersections like cities connected by luminous highways stretching across the cosmos. The cosmic web isn't static either. It's constantly evolving, with matter flowing along the filaments toward the densest nodes, like rivers flowing toward the sea. Galaxies grow by accreting material from these cosmic highways, while smaller galaxies get absorbed by larger ones in a process that continues today. Our own Milky Way, for instance, is slowly consuming several smaller galaxies, and in about 4 billion years, it will merge with Andromeda in what promises to be quite the cosmic collision. Though thankfully, a very slow one. Computer simulations that include dark matter can reproduce this web-like structure with remarkable accuracy, like a cosmic recipe that always turns out perfectly. When astronomers compare their models to actual observations of galaxy distributions, the match is almost perfect, as if the universe followed the same blueprint that scientists sketched on their computers. The simulations show dark matter halos forming first, then attracting ordinary matter, which cools, condenses, and eventually ignites to form stars. It's like watching a city develop in time-lapse. First the infrastructure, then the buildings, then the lights that make it visible from space. But perhaps the most beautiful aspect of the cosmic web is what it reveals about the hidden architecture of reality. Every galaxy you see, including our own, exists because of this invisible scaffolding. The Milky Way sits nestled within a dark matter halo that extends far beyond the visible edge of our galaxy, connected by dark filaments to neighboring galaxy groups and ultimately to the largest structures in the universe. Like a cosmic nervous system we're only just beginning to map. These dark matter halos aren't just passive containers either. They actively shape the galaxies they host, determining how much gas can flow in to form new stars, how fast the galaxy rotates, and even how it will evolve over cosmic time. The visible galaxy is just the tip of the iceberg, the bright part of a much larger, mostly invisible structure that extends into the dark like roots beneath a tree. What's particularly striking is that this cosmic web bears a remarkable resemblance to structures we see at much smaller scales. The neural networks in brains, the mycelial networks that connect forest ecosystems, even the foam structure that forms when you whip cream or blow soap bubbles. It's as if the universe has a preferred way of organizing itself, a pattern that emerges at every scale from the microscopic to the cosmic, suggesting deep principles we're only beginning to understand. And yet, despite its profound influence on everything we can see, the cosmic web remains largely invisible to our eyes. We can map it indirectly by tracking where galaxies cluster, or by observing how their gravity bends light from more distant objects. But the dark matter filaments themselves remain stubbornly hidden. We're like explorers mapping a vast city at night, able to see only the streetlights while the roads themselves remain in darkness, their presence known only by the patterns of light they connect. Long before the first star ever twinkled to life, before galaxies learned to spiral and dance, there were architects at work in the darkness. They weren't drawing blueprints or laying foundations in any way we'd recognize, but they were building nonetheless, shaping the future homes of countless stars and planets with nothing but gravity and time. These invisible architects were dark matter particles, and their patient construction project has been underway for over 13 billion years. The story of how galaxies form is really the story of how dark matter learned to sculpt with gravity. In the very early universe, when everything was still smooth and hot like cosmic soup, dark matter began the slow work of gathering into clumps. It didn't happen all at once. This wasn't a cosmic construction crew working overtime. Instead, it was more like watching a very slow, very large ballet, where dancers take millions of years to complete a single graceful movement. As dark matter particles drifted together under their mutual gravitational attraction, they began forming what astronomers call halos. Not the glowing kind you might imagine around an angel's head, but vast, roughly spherical clouds of invisible matter. Think of them as cosmic snow globes, except instead of fake snow, they're filled with particles we can't see. And instead of being the size of your palm, they're larger than our entire solar system. Much larger. These dark matter halos came in all sizes, from relatively modest ones that might host a small galaxy, to truly enormous ones that could eventually become home to massive galaxy clusters. The bigger the halo, the stronger its gravitational pull, and the more material it could attract. It was like a cosmic game of musical chairs, except the chairs were invisible, and instead of music stopping, gravity kept playing the same patient tune for billions of years. Now, here's where things get interesting. Once these dark matter halos had established themselves, they became cosmic invitations for ordinary matter to join the party. Remember, ordinary matter was still too hot and energetic to settle down on its own, bouncing around like hyperactive children at bedtime. But the deep gravitational wells created by dark matter halos offered a place where this restless matter could finally cool off and collect itself. Gradually, clouds of hydrogen and helium gas began falling into these invisible containers, drawn by gravity like water flowing downhill. As the gas fell deeper into the halo, it compressed and heated up, eventually reaching temperatures hot enough to ignite nuclear fusion. And suddenly, in the darkness of space, the first stars began to shine, like cosmic lighthouses marking the locations of invisible harbors. But dark matter halos didn't just provide the initial framework for galaxy formation. They continue to shape galaxies throughout their entire lives, like invisible puppeteers guiding a very long, very slow performance. The mass of a dark matter halo determines how big its galaxy can grow, how many stars it can form, and even what shape it will take. Small halos tend to host small, irregular galaxies, while the largest halos become home to massive elliptical galaxies that look like cosmic footballs made of stars. The dark matter halo also controls the galaxy's rotation. Remember Vera Rubin's flat rotation curves? Those exist because stars aren't just orbiting in the gravity of what we can see. They're moving within the gravitational field of the entire dark matter halo, which extends far beyond the visible edge of the galaxy. It's like watching dancers perform on a stage where most of the stage is invisible, but their movements reveal its hidden dimensions. Even more fascinating is how dark matter halos influence the ongoing evolution of galaxies. They act as cosmic reservoirs, slowly feeding fresh gas to their galaxies over billions of years. This gas flows along the dark matter filaments we discussed earlier, like a cosmic delivery service that never stops making rounds. When a galaxy runs low on star-forming material, the dark matter halo can provide a fresh supply, keeping the stellar nurseries well stocked. Sometimes, dark matter halos interact with each other in ways that can dramatically reshape their galaxies. When two halos approach each other, their invisible dance can trigger bursts of star formation, distort galactic shapes, or even lead to full galactic mergers. Our own Milky Way's future collision with Andromeda is really a story about two dark matter halos slowly drawing their galaxies toward an inevitable cosmic embrace. The relationship between a galaxy and its dark matter halo is so intimate that astronomers have learned to predict one from the other with remarkable accuracy. Give them the mass of a dark matter halo, and they can tell you roughly how many stars its galaxy should contain, how bright it should be, and even how it's likely to evolve over time. It's like cosmic astrology, except instead of reading star charts, they're reading the invisible gravitational architecture that shapes everything we can see. Perhaps most remarkably, dark matter halos seem to follow certain universal patterns regardless of their size. Small halos and large halos have similar internal structures when you scale them appropriately, like Russian nesting dolls made of invisible matter. This suggests that the same fundamental physics governs galaxy formation across an enormous range of scales, from the smallest dwarf galaxies to the largest galaxy clusters. Computer simulations of galaxy formation have become incredibly sophisticated, tracking the evolution of thousands of dark matter halos simultaneously over billions of years of cosmic time. These simulations can now reproduce many features of the real universe with startling accuracy, creating virtual galaxies that look remarkably similar to the ones we observe through our telescopes. It's like having a time machine for the cosmos, allowing us to watch galaxies grow up in fast forward. But for all our understanding, there's still something deeply mysterious about these invisible architects. We can see their handiwork everywhere we look, in the spiral arms of galaxies, in the way stars move, in the cosmic web itself. But the architects themselves remain hidden. It's as if the universe employed the most skilled builders imaginable, then made them completely invisible once their work was done. And so, as you settle into sleep tonight, perhaps you can imagine the invisible framework that surrounds us, the dark matter halo that cradles our Milky Way like a cosmic nest. Our solar system, our planet, and we ourselves exist within this vast, invisible structure that has been patiently shaping cosmic architecture since the universe was young. We are, in a very real sense, living inside a work of art created by invisible hands, a masterpiece built from gravity and time and matter we cannot see. What is dark matter made of? It's a question that has consumed physicists for decades, like a cosmic riddle wrapped in an invisible enigma. We know it's there. We can measure its effects. We can watch it shape the universe. But when it comes to actually identifying the stuff, dark matter has proven to be as elusive as a whisper in a thunderstorm. The hunt for dark matter particles reads like the ultimate detective story, except the criminal leaves no fingerprints, no DNA evidence, and barely interacts with anything else in the universe. All we have to go on are gravitational clues, the way it bends space-time, pulls on galaxies, and shapes cosmic structure. It's like trying to solve a mystery where the only evidence is the way shadows fall, while the thing casting those shadows remains completely invisible. Scientists have proposed dozens of candidates for what dark matter might be, each with their own personality and quirks. The most popular suspect for many years has been something called a WIMP, a weakly interacting massive particle. Don't let the somewhat unfortunate acronym fool you. WIMPs are actually quite sophisticated theoretical particles that would interact with ordinary matter only through gravity and the weak nuclear force, making them nearly impossible to detect directly. The beauty of WIMPs is that they emerge naturally from certain theories of particle physics, particularly something called supersymmetry. Supersymmetry suggests that every particle we know has a heavier, more mysterious partner particle, hiding somewhere in the quantum shadows. These partner particles would have been created in the Big Bang, but would have mostly decayed or annihilated each other, leaving behind only the most stable ones, potential WIMPs that could account for all the dark matter we observe. But WIMPs aren't the only candidates in this cosmic lineup. There's also something called axions, hypothetical particles so light and ghostly that they barely interact with anything at all. Axions were originally proposed to solve a completely different problem in physics, but it turns out they might also make excellent dark matter candidates. They'd be produced in enormous quantities in the early universe and would still be floating around today, invisible and nearly weightless, like cosmic fairy dust with gravitational pull. Then there are sterile neutrinos, which sound like they've given up on interacting with anything exciting. Regular neutrinos are already remarkably antisocial particles. Trillions of them are passing through your body right now, without bothering to interact with a single atom. Sterile neutrinos would be even more aloof, interacting only through gravity, making them perfect dark matter candidates if they exist in the right quantities. Some physicists have proposed even more exotic possibilities. Maybe dark matter is made of primordial black holes, not the stellar mass black holes formed when massive stars collapse, but tiny black holes that might have formed in the chaotic early moments of the Big Bang. These would be invisible by definition and would interact only through gravity, checking all the boxes for dark matter behavior. Or perhaps dark matter exists in what's called a dark sector, an entire hidden realm of particles that mirror our own world, but interact only very weakly with ordinary matter. In this scenario, there might be dark atoms, dark chemistry, even dark stars and dark planets, all invisible to us, but gravitationally present. It's like discovering that reality has a shadow universe running parallel to our own, close enough to influence us but forever hidden from direct observation. One of the most intriguing recent ideas is that dark matter might be made of something called dark photons, particles similar to the photons that make up light, but with mass and the ability to interact with the dark matter particles the way regular photons interact with electrically charged particles. This could create a rich dark sector with its own physics, its own forces, and its own complex interactions that we're only beginning to imagine. The challenge with all these candidates is that being a good dark matter particle requires a very specific set of properties. The particle needs to be stable. It can't decay away over cosmic time, or there wouldn't be enough left to explain what we observe today. It needs to interact weakly enough with ordinary matter to remain invisible to our detectors, but strongly enough with itself to clump into the structures we see. And it needs to have been produced in just the right quantities in the early universe to account for the cosmic abundance we measure today. It's like trying to find a job candidate who is simultaneously invisible, incredibly long-lived, gravitationally active, and available in cosmic quantities. The universe's HR department apparently hired someone meeting these exact qualifications, but they forgot to keep a copy of the resume. The theoretical physics community has been remarkably creative in proposing new candidates, with names that sound like they come from a cosmic bestiary: neutralinos, gravitinos, chameleons, dark gauge bosons. Each comes with its own theoretical framework and predicted properties, creating a kind of particle zoo where all the animals are invisible and may not actually exist. What makes this hunt particularly challenging is that different candidates would require completely different detection strategies. Hunting for WIMPs requires building detectors deep underground to shield them from cosmic rays. Looking for axions might involve incredibly sensitive magnetometers that could detect their conversion to photons in the strong magnetic fields. Searching for primordial black holes requires gravitational wave detectors and careful studies of how they might lens the light from distant stars. It's entirely possible that dark matter isn't made of just one type of particle, but rather a whole dark ecosystem of different particles interacting in complex ways. Just as ordinary matter includes everything from electrons to protons to entire atoms and molecules, dark matter might have its own rich particle physics, complete with dark forces and dark chemistry that we're only beginning to contemplate. The really humbling possibility is that dark matter might be something so fundamentally different from ordinary matter that we haven't even conceived of the right theoretical framework yet. Perhaps it's not made of particles at all, but represents some completely different aspect of reality. Extra dimensions, modifications to gravity, or physics that only becomes apparent on cosmic scales. As we drift deeper into this mystery, take a moment to appreciate the cosmic detective work involved. Scientists are trying to identify something that makes up most of the universe, while being almost completely invisible to every instrument we've ever built. It's like trying to study ghosts using only the shadows they might cast, or attempting to understand a symphony by feeling the vibrations in the concert hall floor. And yet, the hunt continues with ingenious creativity and stubborn determination. Because somewhere in the quantum foam, in the deepest equations of physics, in the cosmic web that surrounds us, lies the identity of the invisible architect that built the universe we call home. 2 miles beneath the Black Hills of South Dakota, in a former gold mine that once echoed with the sounds of pickaxes and dynamite, scientists are conducting one of the most patient experiments in human history. They're hunting for ghosts, not the supernatural kind, but something potentially even more mysterious. Dark matter particles drifting through the earth like cosmic phantoms, barely acknowledging that ordinary matter exists at all. The Sanford Underground Research Facility is just one of several deep underground laboratories around the world, where scientists have buried incredibly sensitive detectors, hoping to catch dark matter particles in the act of occasionally, very rarely, bumping into normal atoms. It's like setting up mouse traps for mice that are mostly transparent, weigh almost nothing, and hardly ever interact with anything. A task that requires both infinite patience and remarkable ingenuity. Why go so far underground? The answer lies in the cosmic chaos happening above our heads. Every second, billions of high-energy particles from space rain down on Earth's surface, creating a constant shower of radiation that would completely overwhelm any attempt to detect the subtle whisper of a dark matter interaction. By building laboratories deep underground, scientists can use miles of rock as a shield, filtering out most of this cosmic noise and creating quiet spaces where they might finally hear dark matter's gentle knock. The detectors themselves are marvels of precision engineering, designed to notice the tiniest possible disturbances. Some contain tanks of liquid xenon, cooled to temperatures colder than outer space, watched by arrays of sensitive photomultiplier tubes that can detect individual photons of light. The idea is that if a dark matter particle collides with a xenon nucleus, it might produce a tiny flash of light and a small amount of electrical charge. Signals so faint that detecting them requires technology more sensitive than anything used to study ordinary matter. Other experiments use different approaches, each based on theoretical predictions about how dark matter might interact with ordinary matter. Some detectors contain crystals of silicon or germanium, cooled to near absolute zero and monitored for the tiniest vibrations that might indicate a dark matter collision. Others use tanks of liquid argon or specially designed bubble chambers that would show visible tracks if dark matter particles pass through them. The Xenon collaboration, operating in Italy's Gran Sasso laboratory beneath the Apennine Mountains, has built detectors containing hundreds of kilograms of liquid xenon, creating some of the quietest environments on Earth. Their latest detector is so sensitive that it can measure radioactive decays happening inside the detector walls themselves, requiring them to use materials so pure that every component has been carefully screened for trace amounts of natural radioactivity. Meanwhile, the Lux Zeppelin experiment in South Dakota plans to use even larger amounts of xenon, creating a detector so sensitive that it might soon bump up against an ultimate limit, detecting neutrinos from the sun. Regular neutrinos are harmless particles that stream through the Earth by the trillions, but they're so weakly interacting that they've never been a problem for dark matter experiments. As detectors become more sensitive, though, they're approaching the point where even these ghostly particles might create background noise, like trying to hear a whisper while standing next to a waterfall. The patience required for these experiments is extraordinary. Scientists might wait years between potential dark matter detections, carefully analyzing every tiny signal to determine whether it came from a genuine dark matter interaction or from some mundane source of background radiation. Each potential detection must be verified, cross-checked, and compared with theoretical predictions before anyone dares to claim they've actually caught dark matter in the act. And so far, after decades of increasingly sensitive searches, dark matter has managed to remain utterly elusive. The most sensitive detectors have found nothing but empty noise, like fishermen casting their nets into apparently lifeless seas. Each negative result places tighter constraints on what dark matter could be, slowly eliminating possibilities and forcing theorists to revise their predictions. But there are other ways to hunt for dark matter besides waiting for it to bump into detectors underground. Some experiments look for the products of dark matter annihilation or decay, searching the sky for gamma rays, neutrinos, or other particles that might be produced when dark matter particles collide with each other and transform into ordinary matter. The Fermi Gamma Ray Space Telescope and other instruments scan the cosmos for these indirect signatures, looking for excess radiation coming from regions where dark matter should be concentrated. Particle accelerators like the Large Hadron Collider take yet another approach, trying to create dark matter particles in high-energy collisions between protons. The idea is that if dark matter can be produced in the early universe, it might also be created in the extreme conditions inside a particle accelerator. Scientists look for collision events where energy seems to go missing, potentially carried away by dark matter particles that escape the detector without leaving any trace. There are even experiments designed to hunt for axions, those ultralight dark matter candidates we discussed earlier. The Axion Dark Matter Experiment, ADMX, uses a powerful magnetic field and a microwave cavity to try to convert axions into detectable photons. If axions exist and make up dark matter, they should be floating through the laboratory in vast numbers, and occasionally one might transform into a microwave photon that the experiment could detect. Perhaps the most ambitious dark matter hunting expedition is taking place in space itself. The Alpha Magnetic Spectrometer, installed on the International Space Station, measures cosmic rays with unprecedented precision, looking for antimatter particles that might be produced when dark matter annihilates in the galaxy's halo. Other space-based experiments search for gamma rays from dark matter interactions, using the cosmos itself as a vast laboratory. The remarkable thing about all these experiments is that they represent a completely new way of doing science. Traditional particle physics involves smashing particles together at high energies and studying the debris. Dark matter experiments, by contrast, require creating the quietest, most sensitive environments possible, and then waiting patiently for the universe to whisper its secrets. Some of these underground laboratories have been operating for decades, with scientists passing the work from one generation to the next, like cosmic archaeologists slowly excavating the structure of reality. The experiments have become more sensitive with each iteration, but dark matter has remained stubbornly hidden, like a cosmic game of hide and seek, where the universe always seems to be one step ahead. And yet, the hunt continues with undiminished enthusiasm, because somewhere in the quantum foam, drifting through the Earth and through our bodies right now, dark matter particles might be waiting to finally reveal themselves to our patient detectors. Each new experiment pushes the boundaries of sensitivity a little further, bringing us closer to what could be one of the most profound discoveries in the history of science: direct contact with the invisible substance that shapes the cosmos. Until then, the underground detectives continue their vigil, waiting in the darkness for dark matter to finally step into the light. What if we've been looking for something that isn't there? It's a question that makes some scientists profoundly uncomfortable, but it's worth asking. What if dark matter doesn't exist at all, and we've simply misunderstood how gravity works on cosmic scales? After decades of searching for invisible particles with increasingly sophisticated experiments, a small but persistent group of physicists wonders whether the problem isn't missing matter, but missing physics. The most prominent alternative to dark matter goes by the name MOND, modified Newtonian dynamics, and it was proposed by Israeli physicist Mordechai Milgram in the early 1980s. Milgram looked at those puzzling galaxy rotation curves that had everyone scratching their heads and suggested something radical. Maybe Newton's laws of motion simply break down when accelerations become extremely small, like those experienced by stars in the outer regions of galaxies. Think about it this way. We've tested Newton's laws extensively here on Earth, in our solar system, and even in binary star systems where gravity is strong and accelerations are large. But galactic outskirts are different. They're places where gravity is so weak that accelerations are billions of times smaller than anything we experience in daily life. Maybe, Milgram suggested, gravity doesn't weaken with distance quite the way Newton predicted when things get that gentle and slow. In MOND theory, there's a critical acceleration threshold below which gravity begins behaving differently. Above this threshold, Newton's laws work perfectly. Below it, gravity falls off more slowly with distance, effectively becoming stronger than Newton would predict. This extra gravitational strength could explain why stars in the outer parts of galaxies move faster than expected, without needing to invoke invisible matter. The appeal of MOND is its elegant simplicity. Instead of requiring the universe to be filled with exotic particles that no one has ever detected, it suggests that we simply need to modify our understanding of gravity in extreme conditions. It's like discovering that the rules of baseball change when you're playing at very high altitudes. The basic game is the same, but some of the physics works a little differently. MOND has had some impressive successes. It can explain the rotation curves of many galaxies with remarkable precision, often predicting the speeds of outer stars based solely on the distribution of visible matter. It also correctly predicts a relationship between a galaxy's total mass and its rotation speed that was discovered observationally, but seems mysterious in the dark matter framework. But MOND also faces significant challenges. While it works well for individual galaxies, it struggles to explain larger-scale phenomena like galaxy clusters and the cosmic microwave background radiation. These observations seem to require substantial amounts of non-baryonic matter, stuff that's not made of ordinary atoms. even if gravity is modified as Mond suggests. Some physicists have tried to develop more sophisticated versions of modified gravity that might address these problems. One approach, called TEVS, tensor vector scalar gravity, attempts to create a relativistic version of a Mond that's compatible with Einstein's general relativity. Others have proposed that gravity might be modified not by changing Newton's laws, but by adding extra dimensions to space itself, allowing gravity to leak into these hidden dimensions and behave differently on large scales. There's also the intriguing possibility that both dark matter and modified gravity might be partially correct. Perhaps the universe contains some dark matter, but not as much as current observations suggest, with the remainder of the discrepancy explained by modifications to gravity. This hybrid approach might explain why pure MOND theories struggle with large-scale structure, while pure dark matter theories require such specific and hard-to-detect particles. Another alternative explanation focuses on the assumptions built into our cosmological models. When astronomers calculate how much dark matter should exist, they rely on our understanding of Big Bang nucleosynthesis, the process that created the first light elements in the early universe. But what if our models of the early universe are incomplete? What if there were additional physical processes that affected the production of elements or the expansion rate of the cosmos in ways we haven't considered? Some scientists have even suggested that our observations might be systematically biased in ways we don't fully appreciate. Maybe cosmic dust absorbs and scatters light differently than we think, making distant objects appear dimmer and more distant than they actually are. Or perhaps the fundamental constants of physics, things like the strength of gravity or the speed of light, have changed over cosmic time, affecting our interpretation of ancient light from distant galaxies. The debate between dark matter and modified gravity represents one of the most fundamental questions in modern cosmology. Are we missing most of the matter in the universe, or are we missing something essential about the laws of physics themselves? It's a bit like trying to solve a mystery where you're not sure whether the butler did it or whether you've misunderstood the rules of the game entirely. What makes this question particularly challenging is that both explanations make similar predictions for many observations. Both can explain galaxy rotation curves. Both predict that larger structures should form over cosmic time. And both suggest that the universe should look roughly the way it does today. The differences often show up in subtle details that require extremely precise measurements to distinguish. Recent observations have generally favored dark matter over modified gravity, particularly studies of colliding galaxy clusters where the visible matter and gravitational effects seem to be separated in space, something that's difficult to explain with modified gravity alone. But the modified gravity community continues to refine their theories, searching for versions that might explain all the observations without requiring exotic invisible matter. Perhaps the most intellectually honest position is that we're still missing pieces of the puzzle. The universe is under no obligation to be simple or to conform to our theoretical preferences. It's entirely possible that the complete explanation involves both new physics and new matter, or that the truth is something even stranger that we haven't yet imagined. As we continue this gentle journey through cosmic mysteries, it's worth remembering that science progresses not just by discovering new things, but by questioning our most basic assumptions about how the world works. Whether dark matter exists as invisible particles, or whether gravity itself holds surprises we haven't yet uncovered, the universe clearly has more secrets to share. And sometimes, the most profound discoveries come from asking whether we've been looking at the problem in the right way at all. Imagine trying to take inventory of everything that exists, not just in your house or your town, but in the entire universe. It sounds impossible, but that's exactly what cosmologists have been attempting for decades, and their findings are both beautiful and deeply humbling. According to our best current measurements, ordinary matter, the stuff that makes up stars, planets, your morning coffee, and you, represents a mere 4.9% of everything that exists. Let that number settle for a moment. Less than 5%. Everything you can see, touch, or directly detect represents such a tiny fraction of reality that it's almost a rounding error in the cosmic ledger. It's like discovering that your house is actually just a small room in an enormous mansion that you never knew existed, with most of the building invisible and inaccessible to your senses. So what makes up the rest? Dark matter, that invisible architect we've been exploring, accounts for about 26.8% of the universe's total mass energy. That's more than 5 times as much as all the ordinary matter combined. All the stars, planets, gas clouds, and black holes we've ever observed. But even dark matter, mysterious as it is, represents only about a quarter of the cosmic inventory. The remaining 68.3% consists of something even more enigmatic: dark energy. If dark matter is the universe's invisible scaffolding, dark energy is its invisible engine, driving an acceleration in cosmic expansion that scientists only discovered in the late 1990s. Unlike dark matter, which clumps together and helps build cosmic structure, dark energy appears to be spread uniformly throughout space, pushing everything apart with ever-increasing vigor. The story of dark energy's discovery reads like a cosmic detective novel with an unexpected twist. 2 teams of astronomers were studying distant supernovae, stellar explosions so bright they can be seen across billions of light years, to measure how the expansion of the universe was slowing down over time. Everyone expected the expansion to be decelerating, gradually slowing as gravity pulled everything back together, like a ball thrown upward that eventually falls back down. Instead, they found something that nobody anticipated. The expansion is speeding up. The universe isn't just growing larger, it's growing larger at an accelerating rate, as if someone is constantly pressing harder on a cosmic gas pedal. It was like throwing a ball into the air and watching it fly away faster and faster, defying everything we thought we knew about gravity. This discovery earned the 2011 Nobel Prize in Physics, but it also opened up one of the deepest mysteries in science. What could possibly be causing space itself to expand at an accelerating rate? The leading explanation is dark energy, some kind of energy density inherent in empty space itself, creating a sort of cosmic repulsion that overcomes gravity on the larger scales. One possibility is that dark energy is related to something called the cosmological constant, a term that Einstein originally included in his equations of general relativity to allow for a static universe. Einstein later called this his greatest blunder, when Edwin Hubble discovered that the universe was expanding. But it turns out that a cosmological constant might explain dark energy perfectly. The idea is that empty space itself has energy, and this vacuum energy creates a gentle but persistent pressure that pushes space apart. Another possibility is that dark energy is dynamic, changing over time as the universe evolves. This idea, sometimes called quintessence, after the mythical fifth element of ancient philosophy, suggests that dark energy might be a field that permeates space, similar to how electric and magnetic fields fill the regions around charged particles and magnets. This field would have its own energy density that could vary as the universe expands and ages. The truly mind-bending aspect of dark energy is its weakness combined with its dominance. The energy density of dark energy is incredibly small, so small that it has no detectable effect on anything smaller than galaxy clusters. You could fill a volume the size of Earth with dark energy, and it would weigh less than a small car. And yet, because it's everywhere, filling every cubic centimeter of space throughout the observable universe, its cumulative effect is enormous. This cosmic census reveals something profound about our place in the universe. We live in a cosmos dominated by things we don't understand, made mostly of substances we can't see or touch. It's as if we're characters in a vast novel, where most of the text is written in invisible ink, and we're trying to understand the plot based on the few visible words scattered throughout the pages. But perhaps even more remarkable is how precisely we can measure these invisible components. Through careful observations of the cosmic microwave background radiation, the distribution of galaxies, the brightness of distant supernovae, and other cosmic phenomena, astronomers have been able to determine the universe's composition to remarkable precision. It's like weighing ghosts using only their shadows, yet achieving accuracy to within a few percent. The cosmic census also tells us about the universe's future. With dark energy dominating and apparently causing the expansion to accelerate, the cosmos appears headed for what cosmologists call the heat death, a future where galaxies drift apart, stars burn out, and the universe becomes cold, dark, and empty. It's a timeline measured not in millions or billions of years, but in trillions and quadrillions of years, so far in the future that it's almost meaningless to human timescales. Yet there's something oddly comforting about living in a universe where most of reality remains mysterious. It means that despite centuries of scientific progress, we're still at the very beginning of understanding the cosmos. We're like children who have just learned to read, discovering that most of the library's books are written in languages we don't yet know. The fact that ordinary matter represents less than 5% of the universe might seem like it diminishes our importance, but perhaps it does the opposite. We are part of that rare and precious ordinary matter, the stuff that can form complex structures, undergo chemical reactions, and eventually organize itself into stars, planets, and life. In a universe dominated by dark matter and dark energy, ordinary matter is special precisely because it's the fraction of reality that can light up, burn, combine, and ultimately think about itself. As we drift towards sleep, surrounded by this vast cosmic mystery, we can take comfort in being part of something so much larger and stranger than we ever imagined. The universe has been keeping most of its secrets from us, but it has shared just enough to let us know that the story is far grander and more mysterious than we ever dared to dream. Sometimes the most beautiful evidence for invisible things comes not from what we can see directly, but from the way they bend and distort the light of objects far behind them. In the cosmic game of hide-and-seek that dark matter has been playing with astronomers, gravitational lensing has become our most powerful tool for catching this invisible substance in the act of being itself, unseen but undeniably present. Einstein predicted this phenomenon nearly a century ago. when he realized that gravity doesn't just pull on matter, it bends space and time themselves. Imagine the universe as a vast rubber sheet stretched tight, with massive objects like stars and galaxies creating dips and curves in the fabric. When light travels across this warped landscape, it follows the curves, taking paths that appear bent from our perspective. It's as if the universe has been fitted with a collection of invisible lenses, distorting and magnifying the view of everything beyond them. For decades, this remained a beautiful theoretical prediction, with few practical applications. Then, astronomers began to notice something peculiar in their deep space photographs. Some galaxies appeared stretched into long, thin arcs, while others showed up as multiple images scattered around regions that seemed relatively empty of visible matter. It was like looking through a funhouse mirror, except the distortions were telling a story about invisible mass. The first dramatic example came from observations of distant galaxy clusters. These massive collections of hundreds or thousands of galaxies create some of the strongest gravitational lensing effects in the universe, warping and magnifying the light from even more distant galaxies behind them. When astronomers mapped these distortions carefully, they found that the lensing was much stronger than could be explained by the visible matter alone. The invisible mass required to create such strong lensing matched perfectly with predictions for dark matter halos surrounding the clusters. But gravitational lensing offered something even more valuable than confirmation of dark matter's existence. It provided a way to map its distribution directly. By measuring how background galaxies are distorted, astronomers can create detailed maps of where dark matter is concentrated, like archaeologists using ground-penetrating radar to map invisible underground structures. These maps reveal dark matter in exquisite detail, showing how it forms web-like filaments, connecting galaxy clusters and creating the cosmic scaffolding we discussed earlier. One of the most compelling pieces of evidence came from studying colliding galaxy clusters. When two massive clusters crash into each other over millions of years, the collision separates different types of matter in ways that reveal dark matter's true nature. The hot gas between galaxies gets slowed down by friction and electromagnetic forces, creating shock waves and trailing behind like cosmic exhaust. But dark matter, which interacts only through gravity, passes through the collision largely unaffected, like ghosts walking through walls. The Bullet Cluster, located about 3.7 billion light-years away, provides a perfect example of this cosmic separation. When astronomers mapped the visible matter using X-ray telescopes, they found two bright clouds of hot gas marking where the collision occurred. But when they mapped the gravitational lensing, they discovered that most of the mass, the dark matter, had passed right through the collision and was now separated from the visible matter by millions of light years. It's like watching a car crash where the metal and glass get tangled together, but the passengers somehow walk away unharmed and keep moving in their original direction. This separation of dark matter from ordinary matter is incredibly difficult to explain with modified gravity theories. If the gravitational anomalies we attribute to dark matter were simply due to changes in how gravity works, then the gravity should still be centered on the visible matter. The fact that gravitational lensing shows mass concentrations separated from visible matter provides some of the strongest evidence that dark matter consists of actual particles, not just modified physics. Gravitational lensing has also revealed dark matter on smaller scales. Weak lensing studies examine the subtle distortions of millions of distant galaxies to map dark matter throughout large regions of the universe. These surveys show dark matter forming a cosmic web that connects galaxy clusters, creates vast empty voids, and provides the invisible framework upon which all visible structure hangs. It's like using millions of tiny compasses to map an invisible magnetic field. Except instead of magnetism, we're mapping the gravitational influence of dark matter. Perhaps most remarkably, gravitational lensing has allowed astronomers to study dark matter around individual galaxies. By carefully measuring how the light from background sources is distorted, they can map the dark matter halos that surround nearby galaxies, revealing how these invisible cocoons extend far beyond the visible edges of their host galaxies. These observations confirm that galaxies are indeed embedded in much larger structures of dark matter, like visible cities floating in invisible counties. The technique has become so sophisticated that astronomers can now create movies showing how dark matter clumps and flows over cosmic time. Computer simulations predict how dark matter should behave, and gravitational lensing observations can test these predictions by looking at dark matter at different distances, and therefore different times in cosmic history. The agreement between theory and observation is remarkable, like watching a cosmic play where the invisible actors perform exactly as the script predicted. Modern lensing surveys are pushing the boundaries of what's possible, measuring the shapes of hundreds of millions of galaxies to map dark matter across vast regions of the universe. These surveys are so sensitive that they can detect the subtle influence of dark matter structures that are barely denser than the cosmic average, like feeling the presence of a gentle hill while walking across an apparently flat landscape in the dark. The beauty of gravitational lensing is that it doesn't depend on any assumptions about what dark matter is made of or how it behaves. It simply measures the gravitational effects of mass, whatever that mass might be. Whether dark matter consists of exotic particles, primordial black holes, or something we haven't even imagined yet. Gravitational lensing can detect it and map its distribution. It's like having a scale that can weigh invisible objects, providing direct measurements of something we cannot otherwise perceive. As we've journeyed through the evidence for dark matter, from rotating galaxies to cosmic structure formation to underground detection attempts, gravitational lensing stands out as perhaps the most direct and undeniable proof that something invisible is out there, shaping the cosmos in ways we're only beginning to understand. It's the universe's way of signing its name in bent light, leaving gravitational fingerprints that reveal the hidden architecture of reality. Each distorted galaxy image, each gravitational arc, each subtle lensing effect is like a cosmic fossil, preserving evidence of dark matter's influence across billions of years of cosmic history. And as our techniques become more sophisticated and our surveys more comprehensive, these gravitational fingerprints continue to tell the same story. We live in a universe where most of the matter is invisible, but its presence is written in the very fabric of space and time. And so, we arrive at the end of our gentle wander through the cosmic shadows, though really, dark matter's story continues all around us, invisible and patient, as it has been for over 13 billion years. We've drifted from Fritz Zwicky's first puzzling observations to Vera Rubin's revolutionary discoveries, from the cosmic web that connects all galaxies to the underground laboratories where scientists wait in the darkness for dark matter to finally whisper its secrets. We've seen how this invisible substance shapes everything we can observe. The spin of galaxies, the formation of stars, the very architecture of the cosmos itself. We've explored the possibility that it's made of exotic particles with names like WIMPs and axions, or perhaps that we've misunderstood gravity itself. We've learned that dark matter, along with its even more mysterious cousin dark energy, makes up 95% of everything that exists, leaving ordinary matter as a precious and rare ingredient in the cosmic recipe. Throughout our journey, we've discovered that the universe is far stranger and more wonderful than it appears. We exist within vast halos of invisible matter, connected by dark filaments to every other galaxy in the observable universe. Every breath you take, every heartbeat, every moment of consciousness occurs within this hidden framework that we're only beginning to understand. Tonight, as you settle into sleep, perhaps you'll carry with you a sense of wonder for the invisible cosmos that surrounds us. Dark matter flows through this very room, through your body, connecting you to the deepest mysteries of existence. Though we cannot see it or touch it, it is as much a part of reality as the stars in the sky or the pillow beneath your head. And if you found any peace in this quiet expedition through the cosmic unknown, if the mysteries of the universe brought you calm, or if the questions helped you drift gently toward dreams, we'd be honored if you follow us for more journeys through science in the future. Sleep well, fellow traveler in this invisible universe. May your dreams be filled with cosmic wonder and the gentle certainty that reality is far more beautiful and mysterious than we ever dared imagine. Thanks for joining us here at Sleep Science.